Hi everyone, in this video I'm going to talk about correlations between two numerical variables. Correlation of numerical variables. Okay, and then with this concept I'm going to also show you how you'll be able to calculate this using Pearsons R. Okay, cool. Let's get started with asking the question, what does it mean to be correlated, or how two variables are correlated with each other. So to answer this question, we are asking another question such that if a variable increases, right? So if one variable, the value can increases, whether the other variables tend to increase or decrease. Okay, so we are asking the question, if one variable, the value goes up, whether the other variables tend to go up with this variable or tend to go down with this variable. And at that point, we are answering the question about how these two numerical variables are correlated together. And what's important is in this concept here, we are looking at, by answering this question, we're looking for linear relationship. We're looking for linear relationship. Okay, very good. So we're going to do this from two ways. One way is we're going to look from the graph and see how the two variables are correlated with each other on the graph. And then another way is we're going to use a formula to calculate the value of correlation. Okay. So we're going to first we're going to see it from graphs. Okay. So when we say we see it from graphs, the name for this type of graph is called scatter plots. So we'll be looking at scatter plots. Okay. Okay. So this is the new term that we see, scatter plots. Okay. Let me just go ahead and give you an example to demonstrate to you how you'll see from the scatter plots to make your conclusion about the correlation. Okay. So the example we're looking at is husband's age and wife's age. Okay, so basically we have a family. We get the husband's age and then we get the wife's age, and then we're gonna put them together. So the first variable is husband's age, another variable is wife's age. Okay, very good. So let's do a scatter plot and to show you. Okay. So for the x-axis is the values for one variable, and then the y-axis is the value for another variable. So we do the scaling first: 10, 20, 30, 40, 50. Okay, now it keeps going, and then 10, and then 20, 30, and then 40, and then 50. Okay. So let me put a dot here. Let's say 30 and 25 here. Oh, let me say this is wife's age, and then this is husband's age. Okay. What does this dot represent here? This dot represents one family, and inside this family we get the data from this husband's age, and we get the data for this wife's age, right? So here we're saying that 30 is husband's age and 25 is the wife's age, okay? So each dot here represents a family. So each dot represents a family. In other words, each dot contains two values, one from the variable husband, another variable for wife. Okay, cool. So that's one dot. But in fact, in our data set, there's so many families we collected data from, so it's a lot, like many dots. Okay, each dot represents a family. Okay, so there are many dots. And then we're gonna get a line to connect these dots. Say the lines here is approximately the lines here, right? The line doesn't fit all the data points, but it gives you like a direction is trending up, right? So what it means is that, as you can see, as the husband's age goes up, the wife's age tends to also go up. So it's trending upward. In this case, what we're gonna call this, it's positive relationship, right? So husband's age and wife's age, these two variables tend to have positive relationship. In other words, from this scatter plot, we see that husband's age and wife's age, they tend to go up together, and then they have a positive relationship, and therefore they're positively correlated. Okay, okay, perfect. Next, I want to show you an example that two values or two variables, they don't have relationship, or they're not really correlated together. Okay. So example 2, the two variables we have are someone's IQ, right? IQ and shoe size. Student shoe size. And then in this case, we kind of assume that the two, they don't correlate to each other. They have no relationship between IQ and shoe size. Okay, so we just got the plot. This IQ, and this is shoe size. Okay, we say 20, 40, 60, 80, and 100. Okay, and then 10, 20, and 30, right? Okay, so again, I'm gonna put some dots here. Okay, right? So in this case, the way I presented, or the way I drew this scatter plot is that you don't really see any direction in terms of how you can connect these dots, right? So if you connect like this, you kind of connect these 1, 2, 3 dots, it's going up, but at the same time, 1, 2, 3, or 1, 2, 3 is kind of downward, right? And then these 4 points is horizontally. So you don't really get a direction, how these data are trending. So in this case, well, again, each dot represents, say, a person's shoe size and this person's IQ, okay? And then in this case, you kind of don't see any direction from the scatter plot. So in this case, I would say there's no correlation here. No correlation, okay. Which means that if you ask the question, as someone's shoe size goes up, can you predict or can you know whether this person's IQ goes up or down? The answer is no, not really, because there's no clear direction how these two variables are connected. Okay, so in this case, we have no correlation. Perfect. So let me write out the conclusion or summary of what we see here. Okay. So first, positive linear correlation. Okay, so when we talk about positive linear correlation, we're saying that if a variable increases, okay, so one variable increases and the other variable tend to also increase, right? So one variable goes up, the other variable tends to also go up, that's positive linear correlation. And on the opposite is the negative linear correlation, right? And thus, if a variable increases, then the other variable tend to decrease. Okay, so this shows you the opposite effects. If one variable goes up, and the other variable tends to go down, right? So they're negatively correlated. So the shape or the scatter plot is going downward. Okay. Next. Okay. Okay, good. Lastly, the third one is no linear correlation. Okay, no linear correlation. That means you don't really see like a linear pattern between the variables. So there are two possible reasons that lead to no linear correlation. So the first one is the two variables, they're just not correlated. Two variables are uncorrelated, right? So they're just not correlated, or the relationship is not linear. It's not linear, okay? So it's possible that they're correlated, but the way they link to each other is not linear, right? So again, at this point, we're looking at linear correlations. So one variable goes up, whether the other variables tend to go up or go down. Okay, perfect. Good. So so far, we talked about how you'll be able to find the correlation or decide whether it's positive correlation, negative correlation, or no correlation from graphs, from scatter plots. Next, we're gonna talk about the concept, this concept by using calculation from the formula. Okay. Okay. So the final goal from the following calculation is to look for Pearson's R. So we're talking about Pearson's R. Okay. But before we go into Pearson's R, we need to first talk about the concept of covariance. Covariance. Okay. The concept of covariance is looking at answering the question, if one variable changes, how another variable changes with the changes in the first variable. So, or in other words, if you have x and y, two variables, if x changes, how does y changes with x? Okay, cool. So let me give you the formula here, equals to summation I equals to 1 to n, xi minus x bar multiplied by yi minus y bar, and everything we're going to divide n minus 1. Okay. So here's something that we need to talk about is I equals 1 to n. That means with n sets of data points. And then in each set or each combination, we have one x value and one y value. So if we go back to the example of husband's age and wife's age, so each family is one data set. That's one sub data set. That's say I, right? I can be the first family equals to 1, second family equals to 2, but each set has two values, and that's the same in this case. So we're gonna, for each single set, we're gonna take the x value, subtract the sample mean, multiply by the y value, subtract the sample mean for y, okay? And then we're gonna multiply together. So what this part looks at is when x value deviate from its mean, how much does y deviate from its mean, okay? So that's how we can get the co-movement from the two variables, okay? Okay, cool. But why it's n minus 1 here? And then the reason is we're doing inferential. Okay, so we're doing inferential statistics because we're using this sample data kind of to estimate the population covariance. So we are estimating population covariance, okay? Okay, perfect. Let me just go ahead and give you an example and show you how you use this formula here. Okay, so the example is students' study time and their test score. Okay, so now we're looking at two variables. The one variable, the first variable, is how much time the students study for, say, for midterm, and then what's their test scores turn out to be. And we want to ask the question whether they're related, then how they're related. So we're looking at the covariance of these two variables, and then we have 6 sets of data. So it's student 1 hour studying, and the score is 70. 1.5 hours of studying, the score is 77, and then yeah, let me do it here. 1.5 hours of studying, the student gets 84. 2 hours studying, 92, and then 4 hours studying, 89, and then 5 hours of studying, 98. Okay. First, if we want to apply the formula, then we'll have to calculate the sample mean for x and sample mean for y. In our case, we'll need the sample mean for how many hours they study and the sample mean for their test scores. So, so x bar, in this case, let's denote as hour, average, be 1 plus 1.5 plus 1.5 plus 2 plus 4 plus 5, and I'm going to divide by 6, right? So sum up 1, 1.5, 1.5, 2, 4, 5, and divide by 6. This gives us 2.5. Okay, and that's x bar, and let me switch to the right side. Okay, so y bar goes to score bar, which means that the mean of their scores goes to 70 plus 77 plus 84 plus 92 plus 89 plus 98. Divide everything by 6, and that's equals to 85. Okay. So we have x bar and y bar ready, and we're gonna do that. Use that formula. Okay. Let me see. It's gonna be a long calculation. Okay. Let me do it from here. Okay, cool. So covariance. Okay, and we can take each data point. 1 minus 2.5, 70 minus 85. Okay, so this is the first set, right? The student studied 1 hour. Subtract the mean. You got 70 minus the mean. Plus 1.5 minus 2.5. Multiply 70, 785. Okay, and then we're going to continue 1.5 minus 2.5, 84 minus 85, plus 2 minus 2.5, 92 minus 85. Okay, and we have 2 more to go. Plus 4 minus 2.5. 89 minus 85, and then plus 5 minus 2.5, 98 minus 85. Okay, cool. So we're done with this part here. Okay, then we're going to divide n minus 1. So in this case, we have 6 sets, right? So n is 6, but we're doing n minus 1. So 6 minus 1, and this equals to, if we do the calculations, we have 22.5 plus 8 plus 1 minus 3.5 plus 6 plus 32.5. We're going to divide by this by 5. And the result we get is 66.5 divided by 5. That's 13.3. Okay, so this is the value for covariance. We continue from this side. Okay. So we got the covariance close to 13.3. Okay, so this is good. So from now, we see that the covariance is positive, right? So that means they're positively correlated. So if you study more, their score tend to go up. But the question is, what's the unit for this one? The unit, you know, this can be a problem, right? Because when we did the calculation, we use the unit of hours, multiply the unit of points or scores, right? So the unit for this one is hour, say hour multiply score, you know? It sometimes can be hard to interpret, you know, what it means. Okay. And then 13.3, this covariance. If we are doing another example, we're doing something else, right? Say age, husband's age and wife's age, then the unit we get will be age multiplied by age. And at that point, it's really hard to compare the two, you know, whether this set of variables, whether their correlation is higher than another set, you know, just really hard to compare because we don't have the same unit. Okay, but this is okay. Then we're going to use the concept of Pearsons R. Okay, so Pearsons R, or another name for this is correlation. Correlation R. Okay, so correlation R tend to correct this problem because it's gonna help you correct the unit problem, and then it sets a standard value that you'll be able to compare between data sets. Okay. The formula equals to R, it means Pearsons R, covariance divided by sigma hat x and sigma hat y. Perfect. So in this case, we're using the covariance value we get divided by the sample estimation of X population standard deviation and then the sample estimation of Y's population standard deviation, then we'll be able to correct the unit problem here. And let me just write out this one. So this is equals to summation of xi minus x bar squared to n minus 1. Okay, so we learned this in our previous videos. Okay, that's good. Let me give their names. It's the estimation population standard deviation of Y, right? So in this case, it's for Y, but for this will be the same name, but it's for X. Okay, good. Okay, so now we're going to go back and continue doing this example, but instead of stopping at variance, we're going to do one step ahead and calculate for R. Yeah, for R. Okay, so we need to get this and this, because we need the bottom part here. Okay, cool. So instead of S, I'm gonna call this hours. Okay. And then we're gonna get each value, subtract the mean. So we get minus 1.5 squared. Okay, so this value I just already calculated, so it should be 1 minus 2.5. So it's the data point subtracts the mean. I'm trying to save some space here. The same thing. 1.5 and plus. Okay, 1, 2, 3. Let me get it correct. Am I missing? Yes, I'm missing 1. Minus 1 here. Okay, and that's good. And that's 9.5 squared plus 1.5 squared plus 2.5 squared. Okay, and then I'm going to divide by this by n minus 1, which is 5, and then we'll take a big square root of this. Okay, one big square root of this. It's approximately 1.61. Okay, I do the same for the score. Okay, equals to. So I'm going to do square root first. B minus 15. So again, this is the data point, subtract the mean, minus 8 squared plus 1 squared plus 7 squared plus 4 squared 14 squared. Divide this by 5, and then this equals to approximately equals to 10.50. Okay. So we got these two values, and we're ready to apply this formula. Yeah, let me keep the formula here. So R equals to covariance divided by this value and this value. So we have 13.3 over 1.61 multiplied by 10.50. So here I'm going to multiply. Okay, cool. So one thing that I want to mention here is the unit for this one is, say, hour multiplied points. Here, this one, the unit is hour, and this unit is points, right? So the units here and the units here, they cancel out. So this equals to 0.79, and this is unit free. There's no unit for this value, okay? So that's good. You know, we got rid of the unit problem we had. So now let's talk about R, the Pearsons R here. So this value or this index we get is between -1 and 1. So if this value is -1, that means the two variables are perfectly negatively correlated. So one variable goes up by 1 unit, another one's gonna go down by exactly 1. Okay, and then if R is exactly equals to 1, that means the two are 100% perfectly positively correlated. So it's 1 to 1, they go up together. But if R is 0, then that means the two variables are not correlated at all. So there's no correlation between the two. So 0 means no correlation. And then -1 equals to perfectly correlated, right? And then negative, it just means they're negative correlated. Oh no, not perfectly correlated, but perfectly negative. Okay. And if it's negative, that means negatively correlated. Okay. And there's exactly 1, then that's perfectly positively correlated. And then if just positive, it's just positive correlated. Okay, so with this R, then you'll be able to compare the level of correlations between data sets or between sets of variables. Okay, and this concludes the concept of correlation and Pearson's R. And I'll see you in the next video. Thank you for watching.